All right, guys. I guess we're gonna start. The recording is currently not on YouTube, but it's on the MediaTek website. I mean, yeah, that's super helpful for the people who are watching the video. The professor is not here this week, so TAs are gonna do the next two lectures. So today it's me and Soham. Is the sound working fine? Yeah, perfect. So now you should be all perfectly proficient with backpropagation. You've seen gradient descent as a general thing. You've seen how to apply it to a feed-forward neural network. And you've started to see a little bit the problems that come with backpropagation. So next time, the professor mentioned that compared to the perceptron learning rule, sometimes backpropagation can't find the perfect solution in terms of accuracy on the training set, but that it's not necessarily a problem. It can be seen as a feature to enable more generalization and avoid learning outliers. Now we're gonna dig a little bit deeper into problems of backpropagation, but this lecture we're gonna look into the problems of convergence. That is, next time you saw what can be wrong if we manage to get to a minimum of the divergence. Today we're gonna see if we can even get to that minimum, and what kind of problems we're going to find on the way, what kind of solutions we can try to find for these problems. So mainly the two problems are we going to converge where we want to, and how long is it going to be? So if you wanted to do this analysis for a multi-layer perceptron, it would be hard, because these are, as you know, it's a large class of functions that is super hard to, and it's super hard to do optimization with mathematical results on this class. So instead, we're just going to talk about convex optimization problems, which RMLPs are not, but you can consider they're harder. So everything we say today is mostly correct, except for neural networks, it's more complicated. So basically what we're doing is look where we are able to look, like kind of like the guy who searches his keys and just looks where there's light. So a convex function, you know that it's convex when it's curving upward, or that you can also define as you take two for real valued input. Take 2 points on the surface, and you look at the segment between these 2 points, and it should be above the surface at any point. Or you can say that the slope is always increasing. There are a lot of definitions that all mean the same thing. And there are a lot of nice properties about convex functions, one of them being they have only one minimum. So if you manage to get there, you're sure you're in the global minimum of the function. So you can have non-convex function, obviously, and this at the bottom you have an example of one. You can consider neural network error not to be a convex function of the parameters. So for gradient descent, what you want is to converge to a solution. So you say it converges if you arrive at a fixed point. We're not going into the definition of limits of functions and everything. Basically, if you go where the gradient is 0 or closer and closer to this point, you converge. What could happen is you not converging, you're bouncing, like getting closer, not getting closer, just bouncing around this point, jittering, or you can even diverge. So there are conditions to respect to avoid that it happens, because what you want is to converge, right? So you can define, in convergence, you can define the convergence rate, which quantifies how fast you get to your solutions. So you define it as the relative rate of the distance between you and where you want to go at a step and at the step before. So if this rate r is a constant, or if it's like upper bounded by a constant, you're going to say the convergence is linear, but don't get fooled by the name, because that actually means the speed you're arriving at the solution at is exponential, not linear. So I said we are going to look into convex functions. For now, let's start even simpler. We're going to look quadratic functions. That is, functions of, if w is your parameter, you look at something times w squared plus something of w plus a constant. So if you apply gradient descent for that, you're at some point. At the step k, you're at wk. You look at the gradient at this point, you multiply by the learning rate, and you arrive at your next step, wk plus 1. So the question is, what would be the optimal learning rate in this? Ideally, the optimal learning rate is the one that brings you directly to the bottom of the function. So for a quadratic function, it's actually super easy to figure out. You know that you can rewrite your coefficients of the quadratic function in terms of the derivatives, first and second, of the function. That's just Taylor expansion that I think you know about. Do you? If you don't, you can, or don't understand something I said, you can raise your hand, especially if it's a mispronunciation problem. That can happen. If you write your quadratic function this way, you can see that the minimum of the function can be written as compared to where you are, compared to your point wk. You can define it as depending on not only the gradient, that is the first derivative of the function, but also the second derivative. So if you pick your learning rate as the inverse of the second derivative, you're going to arrive exactly where you want in one step. So if you pick an optimal learning rate as this, pretty much. If you pick eta as the inverse of the second derivative in wk, which is actually the second derivative for a quadratic is constant, right? Then at step k plus 1, you're directly at your minimum. So it's not very interesting problem to try to minimize a quadratic function, of course. But we're looking into this more like a tool to understand gradient descent in a general way. So this is your optimal learning rate. If you're smaller than that, what's going to happen is you're going to get closer and closer to your monotonically to your solution. If you're exactly that, you arrive directly there. If you're bigger than that, but slower than twice this optimal learning rate, then you're converging too, but by bouncing from one side to another. And if you're bigger than that, you're just going to diverge. So that's what you want to avoid. Now, if you try to generalize that to generate differentiable convex functions, not quadratic ones, you can pretty much do the same thing. You define the Taylor expansion, except this time it's contrary to quadratic. It's not an equality. It's just an approximation, right? And you can define with the same logic the optimal learning rate as the inverse of the second derivative in wk. And you are actually gonna get divergence in if you take something that's twice that. It's going from quadratics to convex function is not really a proof. So like there's no, we're not proving that that's going to happen. You kind of have to believe us, but it's intuitively you can understand why that's how it works. Because like a convex, you can see it as something that's locally looks like a quadratic. Now, if you look at functions of a multivariate input, more complicated, but that's actually what you have in the neural networks, since you try to optimize with respect to all of your parameters. So that's definitely a multivariate input. So we can still look at quadratics, except this time the form of a quadratic is more like this. So it's WT times dot square matrix dot W plus W dot a vector plus a constant. So if we, for now, let's look at the case where A is diagonal. You already, I mean, if you suppose your function is convex, you already know that A would be symmetric and positive definite. So that's gonna come in handy later. So if A is in addition diagonal, you can also say that the by saying that the Wi are uncoupled. That is, you can move them independently from one another, and it's going to be easier with this curve. So basically, if you look at this curve, which is the equal value contour of your function, the axis, you can see like an equal value contour is basically an ellipse, and the axis, sorry? The axis of the ellipse are parallel to the axis. And in the form of your function, you can see that it's just a sum of independent terms that all depend on Wi. Yeah, so it's basically just a sum of independent quadratic functions. So, if you were to take slices of your function, like vertical slices like this, you'd get different real-valued functions that are basically all the same, but separated by a constant value. And that works for horizontal axis either as well. So basically, the descents with respect to each coordinate are uncoupled. So if you were to optimize each coordinate separately, you'd get different learning rates, and you could do that, and it would work perfectly well. Except that's not what gradient descent does, right? In gradient descent, you'd get a vector update rule, which would look like this. So from WK, you go to WK plus 1 by taking the gradient and multiplying it by a scalar learning rate. And that's it. So you update the entire vector in the direction of the gradient. So, and the gradient would be perpendicular to the equal value contour. So you see that it's not going really in the direction of the of the optimum. The thing is, if there's a big issue with this kind of learning rate of descent, and that's that what we mentioned for real valued input is still true, and you're going to want your learning rate to be smaller than the optimal learning rate. But if you don't want to diverge, it has to be smaller than the optimal learning rate for every coordinate. And since you have a lot, it's going to be smaller to twice this optimal learning rate. Sorry. But since you have a lot, this is likely to be a very small minimum, and your convergence will be extremely slow. And every time the learning rate is bigger than the optimal learning rate, but smaller than twice that, it's going to oscillate in addition. Yeah.
Why is the direction? You said the direction is not going towards the minimum in the 2 slides previous to this one.
Correct.
Why is that? I didn't get it.
Well, in a general curve, if you take the gradient, it's leading to a direction where it descends. But there is no particular reason that if you follow the gradient directly, it's going to lead to the global minimum of the function. So if you, and one property of the gradient is so that it's always perpendicular to the equal valued contour. So here, if you look at it, at this valued contour, you can see that if you take the gradient at the point that we're giving, the direction is not at all the minimum, right?
Okay, so what we're saying is that it works if it's infinitesimal, but if it's like larger steps, then it may like not go towards the direction of the.
If it's infinitesimal, you can say it that way, I guess. It would work if these ellipses were circles instead of ellipses, or that you can, if you look at the definition of this function, if all the ai were equal or equal to 1, then it would work. In general, that's not how it works. That's not a big problem, right? Because you want to get closer to this step, to this minimum in several steps. But the real problem we have is more the question of how fast you're going to get, and the answer is slow. So these are some illustrations of what could happen. Here we are looking at like a two-dimensional input with two different optimal learning rates, still quadratic. So if you're the biggest one is 1, the smallest one eta 2 optimal is 1/3. So if you're a little bit above the double of this second learning rate, you see you're bouncing out of the function. If you're exactly equal to that, you're oscillating without never getting where you getting closer to the minimum. The fastest that you'd go is actually like if you take if your 1 point eta equals 1.5 this, you see you can get fast in the center pretty quickly. But if you take exactly that, then you optimize the second coordinate like super fast, but the other coordinate is gonna be much slower to converge. And if you're smaller than that, it's it's even slower. So here you see that taking exactly one optimal learning rate is not gonna give you the best solution you could. So the rules that were easy to understand in the real value case are not easy here. So convergence behaviors tend to be unpredictable, especially when you increase the dimension. There were a question? Yeah.
On that other slide, was one of those 5 that you were looking at like optimal? It's kind of hard to tell from the picture.
You wouldn't call it optimal. No. If these are your options, I guess the best one is the one on the right. But that's just here. We're gonna try to make a general rules that are better than this a little bit later. But if you want a good learning rate, basically would have to be close to all of your coordinate learning rates. The thing is, if the rate between the biggest one and the smallest one is large, then you're not going to be able to do that, and you can only have slow convergence. So the reason for this problem is that this ellipses that give the equal value contour, they have axes of different length, and that results in different learning rate for different directions. And by the way, that is, we just mentioned the case where A was a diagonal matrix, and that is when the coordinates are uncoupled, but if they are coupled, the thing, it becomes even harder to figure out, because you'd have to take a rotation of this figure, and if you move in one direction, you change the gradient in the other direction. So things become more complicated. So the solution you can think of is to normalize the objective so that you'd have, instead of ellipses, you'd have circles. So that would be taking a change of variables mathematically. So you'd be looking for instead of W, you try to optimize a W hat that you can express as a linear combination of the elements of W, and that you could optimize with the equation at the bottom. That is the equation of a nice paraboloid where the equal value contours are just circles. So if you look at the original equation by just doing some, you're looking at a matrix S such that you could get the equation at the bottom, and it's pretty easy to find that the S you'd get would be the square root of the A matrix. So I mean square root in the sense of like positive symmetric matrices. Are you familiar with that? I guess. So if A is diagonal, S would be diagonal too, and it's just the square roots of its diagonal elements. If it's not, then you still have a square root matrix, and you can get with your updated equation. It's much easier to optimize because now the learning rate is independent of direction. It's leading you directly to the gradient is leading you directly to the minimum, and you can't find an optimal learning rate that would lead you directly to the solution in the quadratic case, right? So if you were to express this equation back into the equation of W and not W hat, what you get is that you have to multiply the gradient by the inverse of the A matrix of your equation. And then if you do just that, the optimal learning rate is simply 1, actually. Because that's the equation on the top is your equation. So if you look at convex functions that are not quadratics, you kind of repeat the same behavior, and you get a sort of optimal learning rate, except this time you're going to replace A by the general matrix of the second derivatives of your divergence, which is also called, you've seen it a little bit last week, the Hessian function of your divergence. So if you just update by the gradient times the inverse of the Hessian matrix with a learning rate of 1, you're going to get not to the global minimum. Let's see what happens, actually. Basically, what you're doing is take a quadratic approximation locally of your convex function. You get to the minimum of this approximation, and then you start again, and again, and you see that that's just an illustration, but here you'd get to the global minimum of your convex function pretty fast. So did we solve gradient descent? No. You still have a couple of very, very problematic issues. And one of them is the Hessian function itself, which is extremely heavy to compute because it has its number of parameters is of coefficients is the square of your total number of parameters in your network. So if you take just a network with simply like 100,000 parameters, the Hessian matrix would have 10 billion items. And you'd have to compute this matrix and then manipulate it. And you can consider that it's unfeasible. And 100,000 parameters is basically what you have to deal with in homework 1 part 1. So it's really not a lot. You'd have to invert this matrix, more importantly, and that's not a trivial operation either, as you may have learned in an algorithmic class. The algorithms to do that are not linear, they are more complex than that. Moreover, it's not, you have additional problems. Since you're not in the case of a convex function when you're dealing with neural networks, you have like additional problem, one of them being that your Hessian function does not have to be positive semi-definite. And if it's not, then if you were to multiply the gradient by that, you could go in the wrong direction in some coordinates, in the coordinates where the, in the directions where the eigen value is negative. You can understand that quite easily, actually. If you just take a if you take a one-dimensional input and you went there, your gradient would go this way, but your curve at this in this section is negative. So if you were to multiply by the second derivative, you'd actually go this way. But for real for multivariate input, you can be sure that this is gonna happen in some coordinates all the time. So the Hessian is not, you can't use the Hessian matrix directly. You'd have to look into the coordinates and avoid moving in the directions where the eigenvalue is negative. It's harder. That's what you have to remember. So is what we did before completely useless? No, you have several optimization algorithms that are evolutions of gradient descent and try to approximate the Hessian matrix and basically do kind of the same thing but with matrices that are easier to compute and manipulate. Here are some you may have heard before. Yeah, there's the BFGS algorithm, the Levenberg-Makar algorithm. You see them quite a lot in machine learning in general, but in neural networks, not so much today. You used to see them. Now we find more stuff that seems to work better. So most of what you're going to see next and Wednesday are examples of algorithms that are that apply well to neural networks. Other issue, the learning rate. So we saw that if you wanted to avoid getting out of getting away from your minimum, you had to have a learning rate that is smaller than twice the optimal learning rate in this convex curve. But since neural networks are not convex, actually getting out might be exactly what you want. Like if your initial point was like in this area with this local minimum, you'd rather not get to this minimum, but have a learning rate that's big enough so that you can get out and get to another lower minimum. Getting to the global minimum in general is not reasonable, but what you want to, where you want to get is a good local minimum. So if you have a big learning rate, it can help you escape local optima. But if you had always a big learning rate, then you'd never actually reach your local optimum, your an optimum. You'd just bounce around and never converge. So you kind of have to find the happy balance between these two phenomena. So what you usually do is just decay the learning rate. So you start with a large one and you gradually reduce it. So you have a lot of ways. Like here, this shows what will happen if you were to do that. So basically, that's what you want, right? You get out of the bad minimum and you went into a good minimum. So to decay your learning rate, you have a lot of ways to do that. You can do it regularly at a linear pace, a quadratic pace, several possibilities. What you will usually do in practice is simply take a constant learning rate, you train with it. At some point, you see that you stopped getting better. Your training loss or your validation loss, better, is stuck. Then you just divide it by 10, and you you start training back where you stopped, and you do that a couple of times, 3, 4, until you don't move at all. So that's it's not necessarily what's best, but it's super easy to implement, and it tends to work fine. So that's where we are right now. We saw some of the convergence issues, some related to solutions and problems dealing with second-order method. That just means using second derivatives. So that's all the part with the Hessian matrix. And the problems related to the learning rates and how you can solve that. So that is all for my part. Who's doing next thing? Oh, we don't have SOAM. This is bad. Don't know where it is. Okay, we kind of have a problem of structure right now. You're familiar with AirProp? Okay, you can try that. All right, so this is a very good time to take questions, if you have some. Yeah?
Are there large gains from starting from large steps and then going higher steps? In your experience, I mean, all of this.
In my experience, yeah. I mean, if you take, for example, the homeworks in this course, it can make a fair difference. I mean, if you start with a super high learning rate, obviously you're not going to learn anything. Usually, you start with something like 10 power minus 2 or 10 power minus 3, and at some point you stop improving. And then you, the first time you're gonna decay your learning rate is gonna bring some strong improvement. A second time can bring a little bit of additional improvement, and then you just get stuck in general. So yeah, it's not a theoretic tool. It actually works. Anything else? For anything that was before? All right, so we're just going to see if we have a solution to this problem. Otherwise, I guess I'll. Yeah.
I don't know if you have said this before, but how do you set your initial learning rate? I mean, you will decay it, but how do you set the initial?
It's kind of a handmade tool. I mean, I guess you could, if you know it's you're evolving in a space with this dimension, you know what kind of running rates tend to work in this case. Usually 0.01 or 0.001 are the ones you start with because they are small enough that you're going to get some initial progress and they leave the room for decaying a couple of times. All right, so I guess I'll just try to go further. So if you take a step back, instead of, we're going to see like a couple of algorithms that are doing something a bit different from gradient descent and are kind of better, working better with respect to the problems we mentioned. So you saw that the problems arise because we need a fixed step size across all dimensions, and since you need separate ones for the different coordinates, that's where the problem comes from, and that's why you need to scale the axes and everything. If we, instead of scaling the whole space, we can just try to relax these requirements and see algorithms that don't exactly use the derivative of the whole function. Kind of do that, but not exactly, and tend to be efficient for neural networks. These are not the ones you see the most in the literature, but some works tend to show that they work as well as anything else. So it's really worth knowing that they exist. So RPROP is short for resilient propagation. It's a super simple algorithm where you basically follow a separate gradient descent for each of your coordinates. So at okay, cool. Are you very familiar with RPROP by any chance? No, okay. I'll just try to keep up that. So basically, what you do is at each time you're gonna go in the. You're gonna look at whether you went in the right way or not, and if you are, you're just gonna go the same way by increasing the step, and if you're not, you're gonna go reduce the step and go the reverse way. So it's kind of looking at whether you were doing a monotonic convergence, in which case you can afford to go faster, or are you in a bouncing out case, in which case you want to go the other way, but slower to avoid getting out of your minimum of the local convex zone. So what you take is you select an initial value, W hat, and you take a step at first. Basically you take a step in the direction, general sense, of the derivative. But that's a single valued, we're looking at it in the one-dimensional input case. So you take, you go in the direction of the derivative, but at first you go in this direction, and you see whether it reduced the function or not. So that's what you do at step 0. What you do at step 1 is, if in the previous case you were going in the if you were going in the right direction, that is, if your value decreased, then you're just gonna go this way, but faster. So you multiply your step size by like a constant coefficient, alpha, and you keep on. And you do that until you actually got a bigger value at one step than you had at the previous step. So that means you're going, now you're going the wrong way, so you just go back. Oh, you're even bigger now, so you're just gonna go back the initial way. So you have few parameters here. You just need the increasing coefficient alpha and the decreasing coefficient beta, and that's about all. So as you see, you don't really need to compute the gradients here, right? Because you, if you're in a one-dimensional case, the gradient is just the direction. The derivative is just giving the direction. Here you have the algorithm itself is going to tell you which direction to go. So you just need to compute the derivative in the initial step. And there you just apply the R-prop iteration, and you don't need the derivative anymore.
If you were, sorry.
Yeah.
If you don't calculate the derivative again, how do you know if you're going still in the right direction?
Because what you use to know if you were in the right direction is not the derivative, but the difference between the value you had at this step and the value you had at the previous step. Which, so the increasing, what do you call that? The increasing rate, yeah, which is this thing that can be positive and negative, and that the derivative approximates locally. You just look at that, and that's all. That's what makes the derivative interesting. The thing is, if you want to do R-prop for a multi-dimensional input, what you do is just apply the R-prop algorithm for each coordinate separately. And you do that until, for each of your layers, for each of your coefficients, you apply what we just said. And you do that until you appear to have converged, pretty much. Yeah, so as you see, you just used the backpropagation algorithm to compute the derivative at the initial step, and then you use R-prop to do all the next steps. So the idea is that you do R-prop for each coordinate, then separately, and then you start again, because of course you moved, since you moved, it's not like you can update the coordinates separately and you're going to arrive at the minimum. But let's say you have like a two-dimensional algorithm. So W1, W2. So that's how you start. So you apply, you compute one derivative. You apply R-prop to W1. And W2 doesn't change. Then you apply R-prop to this one. And then back to this one. and you do that, and so to go from here to there, it's just one backpropagation and several iterations of our prop until you reach some like level of convergence where you don't increase at all from one step to another. And so this, which is actually simple and you'd expect not to be super efficient, tend to be actually super efficient. And what is great is that it is not even a second order method like the Hessian thing. You just look at the increasing rate for your function, and it tends to be much better than gradient descent. Makes me a little assumption about the last function. Yeah. So you just, you pretty much don't make any assumption at all. You don't even need the function to be convex for this to work. That doesn't mean you're going to get to the global minimum, right? But you're going to get somewhere, and it tends to work. No, as for quick prop, yeah.
So we have to keep a vector of learning rates, one for each dimension in our prop?
Keep a vector of learning rates, you say?
Because all the learning rates for different dimensions might be updated at different times. Which means we keep not one learning rate, but
well, you don't.
one for each dimension, right?
You don't really keep them. You, since you're going to modify this coefficient with like its step size that you have to remember, then you move to once you're quote unquote done with W1, you update W2.
But instead of like 1, you would have n learning rates.
Well, you can't really say that because it's not like you move them all together with separate learning rates. You just use a so-called learning rate for this one, then you forget it and you move along to the next parameter that you want to modify. And when you go back for additional updates of W1, you start over. You don't take back the steps that you the alpha and beta that you remembered from the initial modification.
Train each dimension separately?
Pretty much, yeah. Separately, but since they are not independent, that's why you have to do that several times. Right? If you just stop there, you'd not have reached anything that looks like a minimum. But if you do that like 10 times, 50 times, in the end, you're in something that looks like a minimum.
So each time we only update one parameter?
Yeah. And each time you update one parameter, then the next one, and then you start over.
And we only calculate the divergence, like the derivative of the divergence with respective to these parameters.
Yes. But the thing is, if you want to compute the derivative of a parameter that's like on the first layer of your network,
Yeah.
you have to do the whole backpropagation basically, because all of the coefficients on the second layers and the later layers depend on this one parameter. So you, in this diagram, you compute backpropagation at every of this step. Here you backpropagation once, here you do backpropagation once, etc., etc. So you do much less backpropagation computations than you would with gradient descent. Other questions about our prop? So quick prop is is based on the Newton updates. That is the gradient descent with rescaling by the invert of the Hessian matrix, everything we talked about. There are just a couple of big modifications. One of them is dimensions are independent, kind of like our prop. So these are two methods to kind of uncouple the coordinates. So in quick prop, you just you use the Newton update for each dimension separately. So you'd compute the second derivative of the divergence with respect to one of the WIs. So this is actually, you may think that if you do that for all of the parameters, you need to compute something that's as big as the Hessian, but that's actually not true. It is less expensive to compute, even if it's not like completely obvious. And more importantly, the reason it's more simple than computing second derivatives is that you're gonna approximate that with finite differences. Kind of, in a way, what you did with R-prop with the derivatives, like you sort of approximate the derivative by looking at the finite difference between two values. With quick prop, you're gonna look at you're gonna try to approximate the second derivative the same way, but you still compute the exact derivative, first order derivative, but you're gonna approximate the second one. So you do that pretty much this way. You just you compute the derivative. The second order derivative is going to be approximated by the difference between first order derivative at WK and at WK minus 1. Divided by the difference between the two. So that's exactly what finite difference is. So since you compute the first order derivatives with backpropagation, you don't need to compute anything else. You just take so the difficulty is just that you have to remember your derivative from one additional step. Is it clear up until now? Basically, what's amazing about this algorithm is that although that's not necessarily what's best for reasons that are going to be clearer Wednesday, they are very simple and both very efficient. So, yeah. So the first order derivative is just a backpropagation, and that's all you need. So here you'd use coefficients that come from two different iterations of backpropagation, the last one and the one before. It's not that easy to use with PyTorch or TensorFlow or this kind of frameworks that are not really designed for that, but it's manageable. And if you were to do that for one homework, there is a chance that it's gonna give good results. So you can try, and actually, if you manage to get good results with that, it would be quite interesting, and there's room for a publication to do that actually. So it has some problems. Quick prop, it's a little bit unstable in the general case, so the non-convex case, but still it's. It tends to be very fast and to work in many cases. So that's pretty much where we are. So what we're going to see now are, I think it's momentum, right? Yeah, UP. They do. Okay, so the famous momentum that you've all seen in homework 1 part 1 is another way to solve some problems of gradient descent. So we go back on regular gradient descent this time. So you have yes, so the solutions we mentioned to have like a dimension-independent learning rate, they are efficient for some reasons, but still have some problems, like the fact that you tend to oscillate in the directions that you're not looking at some point. So one momentum is a way to keep track of the oscillations and of the general direction you're going to, and to emphasize the steps in the directions that tend to, in the previous, in the directions that seem to converge. So it's kind of a memory-based update on gradient descent. So the basic idea of the momentum is to keep a running average of all of your past steps. The idea being that if so you keep a running average in every for every coordinate, right? It's you keep a running vector average, except in the directions where you had oscillations, the previous steps are gonna tend to negate each other. So you by keeping a running average, you're negating the direction in the update in this direction, and you're just moving in the directions where you actually get some progress. So that's kind of the idea. If you used regular gradient updates on a function with equal valued contours like this, most of the updates would be in the direction, in the vertical direction, where you have little improvement. And if you you add a bit of momentum to that, you're gonna emphasize the direction, the updates in the direction that is actually making progress. So the general direction of convergence. So you do that simply by you maintain a running average at this point you should be pretty familiar with that. So you to get the step size at at step k, you just multiply the step size as step k minus 1. You multiply that by a coefficient called beta, that's usually 0.9, but it could be something else, and you add to that the step size that gradient descent gives you for step k, and that's all. It's actually very simple, and it increases directions in the it increases the step size in the directions where the gradient tends to stay the same size, instead of the ones where it flips. So the updated gradient descent rule is super simple to write. So that's gradient descent in general, and that's gradient descent with momentum. So barely anything changed. You just have the running average to keep track of. So that just So if you look at it more closely at the step level, here with the momentum update, it's kind of like you compute the gradient step at the current location, and then you add the scaled previous step. You can do the opposite if you think about it. Like you compute, first you move to you move according to the running average to a new location, and then you compute the step size from that point, and you get the final step. So if you do that, it's a little variation on momentum that's called Nesterov accelerated descent. So you see, you extend at every step, you extend the previous step, you look where you are, you compute the gradient there, and you get your final step like this. You just, in the end, it's like you added the two, and so it's close to momentum. It just the difference is just where you compute your new gradient. So you have to slightly change the momentum, the update rule for Nesterov. So if you compare Nesterov and momentum, you see that in a lot of cases, Nesterov tend to be actually better, interestingly. So it's actually not as common to find in deep learning frameworks, but it's there are reasons to believe that it's actually better. So where are we? I think, yeah. So this was actually all for today. So what remains to see is incremental updates, what's also called stochastic gradient descent. And how we're gonna revisit all that we've seen based on that, and some tricks for generalization, etc. We apologize for the bit of confusion for the second part of the slides, because yeah, that's not the part that I was supposed to do, but so may have seen a little bit drafty. Sorry about that. But if you have questions, we have still some time to answer it. Like. Technically, there's still 10 minutes of class. Yeah.
Why is quick faster than normal gradient descent? Because you still need to calculate the entire gradient.
It's but the thing is, it's not that it's faster than gradient descent with the Newton update. But contrary to the version with the Hessian matrix, quick prop you can actually compute, right? Because you don't need to compute the matrix of the second derivatives. So the difference is not in number of steps, but in the computational power you need to actually do it.
It's a second order.
That's a second order method, but with an approximation of the Hessian matrix. Kind of like the thing we mentioned, LFB, LFGS, etc. So there are a couple of hidden slides in there that the quiz will talk about. You should remember that.
What topics are these?
Just some additional problems with the Hessian. A little. It's not like one big thing for this one. For the next lecture, you're gonna have a whole part about the generalization of our prop that's not covered in lecture.